Okay, we can start now.
Should I introduce, or we all know each other?
I think we all know already each other.
So how many people are there? We only three?
Four of us. Nikhil, you, Richa, Gyan.
I am also here.
Okay. So should I start?
Yeah, you can start.
Okay. So today I will give a talk on a very fascinating topic. Actually, in 23rd June, his birthday was there. So I decided to give a talk on Alan Turing. So Alan Turing was a British mathematician, and he was not only mathematician, he has given contribution in many areas like computer scientist, and he has done many decoding and crypto analysis of many different areas. So the main decoding he did was of a very special machine which was used by German Navy and German how should I say army, Enigma machine. Me and Gyanti sir saw one movie. What was movie name, sir?
I think Enigma.
No, the movie name was Imitation Game. The
Imitation
machine
game.
Yeah,
Machine
the
name was Enigma.
machine name was Enigma machine. So I will give the movie title, and because it was a very beautiful movie, very good movie. So he was actually considered as the father of theoretical computer science because may not in experimental way, but in a theoretical way, he has given many theorems and models for the deciphering and giving the solution to many problems. So he is not only known for the deciphering the Enigma machine, but also Turing patterns, Turing reduction, and reaction diffusion model. So how he was curious about the combination and the connection between the mathematics and the nature. So first of all, he saw that there are some patterns and the growth of the skin pigments and the nature of the growth of the some special category of animals of limbs and the particular thing. So he was curious that how these things are only based on the biological growth. There must be some mathematical formulation with which we can already guess, and we can tell that how this growth and the development of a particular pattern is happening. So in that basis and in that curiosity, he gave one particular theorem, which in a very normal way, it is called reaction and diffusion, or in other thing, in another way, it is also called Turing instability. So in Allen's mind, it came in 1952, he wrote a paper. In bottom, I have written the chemical basis of morphogenesis. So in that paper, he has given that on the basis of mathematical equations and the particular in a particular chemicals, if we see, then we can formulate and we can tell that how this growth is happening in a particular form or in a particular animal or a human being. So in the organism also, and at that time when he wrote the paper, he did not tell anything about that how these things can also be used in artificial intelligence or in the artificial world. He only told that these things and the development in the organism can be explained on the basis of mathematical formulations. But later, after at that time, he was not given as much recognition. But later, nowadays, we are mimicking the biological patterns and biological behavior on our many artificial intelligence. So nowadays we are giving more recognition to Alan Turing theorems and their instability theorem rather than the previous class. So the magic of chemicals means he basically said that if we think about the growth of a pigmentation or a pattern on the skin of a animal, so there are basically two set of molecules which he called activators and inhibitors. So activators were behaving like a positive contributors. You can say positive on the basis of that it's happening in a pattern basis. So activators increases the chemical activity and inhibitors reduce the chemical activity. So if you see the change on the basis of pigmentation, so if we the creation of the pigmentation occurs in the region where activators are more rather than the inhibitors. So if I have included these slides so that we can see in the mathematical way also that how these activators and inhibitors we can compare on the mathematical basis. So basically it is called reaction diffusion model or the Turing instability. So if we take a system where we have two reactants, so one reactants have a rate of diffusion, or sorry, the concentration U, and the other reactants had a concentration V, and we write the dynamics of both the reactants at a function which depends on U and V, and we take a fixed point U star, and V star is the fixed point. And if we expand the solution in Taylor series around the fixed point, so this is a J is the Jacobian, and the condition of the stability is that function of the depending, which is depending on the U and the function G, the trace of the Jacobian should be negative. So this is the condition for the stability. If we add the diffusion, so this is du is the diffusion coefficient and the Laplacian of U, this is the addition of the diffusion. So the first is the reaction and the second part is the diffusion part. So blue one is the reaction part and the second part is the diffusion part. So that's why it is called reaction diffusion model. So if we include the perturbation in our system in a slight way, so in the perturbation form where the two equations are written, I can in iPad I cannot show the cursor. So that lambda t is basically the growth of the perturbation. So if lambda is positive, the perturbation is more. If lambda is negative, the perturbation is less or the stability is more. So how these stability conditions and the instability conditions are given.
Sorry,
Yes,
Nikhil.
sir. Yes, sir.
You said when lambda is more, the perturbation was. I think you wanted to say that when lambda is positive, the perturbation will grow, and when lambda is negative, the perturbation will decay.
Will decay. Yes, sir. That's
Okay,
what
okay.
I want to say.
Okay.
Yeah, I was saying that if lambda is negative, perturbation is decay or the stability is more. And if lambda is positive, the perturbation is more.
How is stability related to lambda? I mean, lambda being positive or negative? Because even if so, I would suppose stability means the state is not changing. State of a
Yes,
system
sir.
is not changing. So even if lambda is negative and the perturbation is decreasing, how, in what sense it is stable?
Means if we are perturbing a system in a more extent, it means we are decreasing the stability of the system already, right?
That is okay. That is okay.
Yeah.
But my question is, you say that when lambda is negative, the system is more stable. Is this what you said?
Means it's my point of view. I don't know if mathematically it is correct, but if perturbation is decaying, it means we are going towards the stability more, right? Means
I mean,
at the
asymptotically
initial,
you're reaching. I mean, perhaps
Hmm.
asymptotically you're reaching to something. Okay, it happens.
Yes.
It may happen in this case.
Yes, yes,
Infinity
yes.
minus t. But then, okay. So I was wondering what happens when you take the limit t goes to infinity. When lambda is negative, what happens when you take t goes to infinity? So if you do that, then delta ut will go to 0. So is this what the condition for stability or not?
The stability condition is that the trace of that function, the trace of that Jacobian, its fu plus gv should be negative. Means they individually they should be negative and the summation should be negative. When we are going towards instability, then the one of them will be positive, but the negative part magnitude will be more, and this condition will be followed, but one of them will be positive.
And fu means derivative of f with respect to u.
With respect to u.
I mean the partial derivative.
Partial derivative with respect to u, and gv is partial derivative with respect to v.
Okay. Okay.
So what is the condition of instability? So there are two conditions. One is necessary condition and the other is which I will show in the next. It is the sufficient condition. So necessary condition is if we think about the trace, the fu and plus gv is negative. But there are two possible cases that win-win. In the first case, both are negative. In the second case, one of them is negative, but the magnitude is more. So overall, it is negative.
Okay.
So in first case, we cannot have cannot be positive. This case square FUDV, that diffusion coefficient, this cannot be positive for the first case. So we will leave that case. In second case, we can show the instability. So if we take FU is positive, GV is negative, but the magnitude is more of the GV. So the overall FU plus GV will be negative. So they will satisfy that condition that trace should be negative. So this will lead towards the necessary condition for the instability. But this is only necessary condition. The sufficient condition, we will have to clarify the diffusion part also. So if we expand that variable in Taylor series about that fixed point, which was U star and V star, so we can write that perturbation in terms of Jacobian with the diffusion. So in the second slide, we have d delta U by dt is equals to Jacobian with the diffusion in delta U, where delta U, that's yes sir.
Sorry.
Yes, sir.
So how did you define U star and V star? I mean, how did you get this point?
In a very general way, we have defined in a particular system, we have many fixed points, but for a initial purpose, we have taken a single fixed point where there is no diffusion. Means wherever reactants are, they are stable with the point. They are not going anywhere. They are not diffusing. They are not mixing.
Okay, I have another question. Has it something to do with the chaos theory? Because if I remember, there are some kind of maps in chaos theory in which, I mean, so depending upon the initial conditions, the system approaches some fixed points. So has it something to do with that chaos theory, or I mean, what is the meaning of a fixed point?
Actually, honestly, sir, I have not read chaos theory exactly, so I don't know if
at
it
least
is
in this context.
really.
Sorry, at least in this context.
In this context, actually, in that I have seen one or two lectures which was given by Suhadeep by IIT Kanpur. One research scholar was there. So he has just defined that we have a starting point where we have taken that the whole system is stable. We have two reactants, but they are not going to diffuse or mix or going to go anywhere where instability can be proven. So I don't know if it is really similar to chaos theory or how it can be matched, but he has given a simple formulation like that. Because I have not depth knowledge of chaos theory or any this model. I have just read recently that how is it working.
Actually, I mean, so that maybe it may not have anything to do with the chaos theory, but I was like wondering.
Maybe.
So I mean, so.
But it can be relatable. Maybe it's not similar to that, but it can be relatable.
No, I mean, perhaps I missed that. I mean, I did not, or I mean, you said something about, or you gave the definition of a fixed point, but perhaps I missed it. So was that in the previous slides?
This was U star and V star was fixed point.
Okay, sorry,
that function is going to be.
I missed it. I'm sorry.
Oh, you have seen. Maybe I haven't given that a specific time for that fixed point and all.
Yeah, because I did not see this definition.
Okay.
Now I saw it. Okay, thank you.
Okay. So if we analyze that diffusion part, so now we can write the Jacobian with that minus k square du term and minus k square dv term. So we have included that diffusion coefficient and the diffusion part also in the Jacobian. So now we can write the trace and determinant of the J with the diffusion thing. So now the trace is the previous trace minus k square bracket du plus dv. This is also negative, means less than 0. And now in the determinant, the determinant part, we have one additional term which must be positive for instability. This k square fe dv gv. Basically, it will be positive because k square will be always positive, and if we are taking the diffusion, that du and dv will also be positive. So the first thing was the necessary condition, and now we have the sufficient condition. If we plot that determinant lambda t and versus k square, this range of unstable mode we are getting. So if we plot this thing, the determinant of JD, this range will give that what unstable modes we are having. So this condition is the sufficient condition for instability or the Turing stability which he gave. So that was the mathematical part which we can read how he was giving. This was a very general thing when we say that we have inhibitors which will reduce the chemical activity, and we have activators which will increase the chemical activity, and this was the mathematical explanation of that. So what are the conditions when we are getting a special type of patterns in our day-to-day life? So we see stripes pattern, we see dotted patterns, we see labyrinth patterns. So if inhibitors which are decreasing the chemical activities are less than activators, we get stripe patterns. If we have inhibitors which are more than activators, we get dot patterns, and if they are equal, we get labyrinth patterns. So the first is stripe patterns. So stripe patterns means activators are more. In dot patterns, the inhibitors are more, and in the labyrinth, both are same. So that's how, in a very general way, these patterns are formed on the basis of that two chemicals which are taking part, especially on the pigmentation, on a pattern on the skin, on in a very general way.
Okay.
So
Can I
this
ask a
was,
question? Can I ask a
yes, sir.
question? Can you
Yes,
please
sir.
go to the previous slide
This one?
in which you showed stripes, dots, and labyrinth? Yes. So
Yes, sir.
as you say that if some conditions are satisfied, that if inhibitors, depending upon whether inhibitors and what was the other one?
Activators.
Activators, yes. So depending upon activate whether inhibitors or activators, I mean their ratio, you get stripes, dots, or labyrinth. So I
Yes, sir.
can see that for example, zebra has stripes, maybe
Yes, sir.
leopard and other cats have dots on them. And where do you see the labyrinth structure in the nature? On what kind of animals?
That I can tell you, sir, very good example. Like it's not a exact, this will happen every time, but some art, some artists do a burning of the wood. If you have seen, they will take a very fine sheet of the wood and they will put a very high current on the both end, and the some of the part wood of will burn. Have you seen that art?
Yeah, I mean,
So
okay.
so in that art, sometime you can see that labyrinth pattern, or basically that labyrinth pattern we can see in game puzzle, where you will have to go from one end to another end. You will have to enter from one side and come from the outside.
Actually, my question was so that
So
you
naturally, where you are getting these things, you are saying.
yes.
So naturally, I cannot say that's a natural way, but one example which was given during the Australian bushfire. So in Australian bushfire, you can take like the forest was on burn. So that fire was like a activator, and the response team which was spraying the water with the helicopter and all, they were like inhibitors. So if both are giving the same contribution, you can get that labyrinth pattern, or you even can get these all of the patterns in these conditions. That's a very particular example where you can get all these patterns in natural thing, in the natural in the that dynamic phenomena. Actually, patterns are a very stable phenomena, they don't change with the time, but that example, it has been taken as a dynamic phenomena.
Okay, so
Should I give an example like in written form?
no, that's okay. So my question is, so do you see as you just said that in the case of Australian fire, that fire was what from
But we cannot say that thing as a pattern, because it's a dynamic incident, it's not a pattern.
okay.
These particular things are pattern, and you are true, because I have most of the time I have seen that labyrinth patterns in artificial way when they grow the grass in a particular pattern and all.
Yeah, because that is not happening by itself, and somehow in the case of stripes and dots, there are some differential equations
Because I cannot say 100%, but because maybe naturally it's very rare that both the inhibitors and activators are in same quantity on the same extent.
Okay.
If Hina would be there, he can tell that the our tooth formation, na. So our tooth formation, every tooth have a specific position and a specific shape, molar, antimolar, and sorry, premolar, and the front side
Incisors
teeth.
and
They have a
eyelids.
specific shape, right? So when these tooth will grow,
Okay.
before tooth formation, there are two layers which will control the shape of the tooth.
Oh, okay.
So their two layers are activating as a activator and the inhibitor. So one will reduce the shape and one will not reduce. One will reduce the growth and one will increase the growth. So that's how they will particularly grow and make a shape. After that, the tooth will form. So in biology, the Turing instability was used in many cases. Like there are two animals, mouse and vole, I think. They look similar, but their teeth are very different. So that was because of Turing instability. The second thing, in limb formation also, that instability is used because we need a particular direction for the bones to grow. They cannot grow in any direction. So in that, the as well as activators, inhibitors are also have a very key role, that they will not let the bones to grow in any direction.
Okay.
Yes. So this was just the organism where we used that Turing instability, but at that time he only worked on the paper that the growth and the patterns can be formulated and can be explained on the basis of mathematics. But nowadays scientists have also got the idea, and they have used the Turing patterns and the Turing instability to mimic the organism things in the 2D patterns, or where we are giving a particular fingerprints. Like you see the different thousands or millions of QR code daily we are using, and that's actually a mimic of the natural phenomena and the organism. They code the different codes of the animal and the semi-arid landscape. Semi-arid landscape means that landscape which is not totally barren. There is some part of the rain, so there are here and there some bushes are there. So previously people were thinking that the growth of these bushes are really random, but later they got to know that's not a random, because some part we are getting the rain, some part rain is not there. So where rain is there, it is a activators for the trees and the bushes to grow. Where rain is not there, it's like an inhibitor. So all these things, all these phenomena, nowadays we can go back to this paper and we can explain it by this. So in real life there are so many examples for this thing. So like first picture is a zebra fish. So from the mouth to the tail, this fish has a pattern which is a zebra type, sorry, stripe type patterns she is having. The feather of peacock is also having a particular type of pattern. The whisker growth of mice and the pattern of sail, all these follow the Turing patterns. So additionally, scientists have found that those chemicals which he described, activators and inhibitors, they can be the reason why these special birds have their feather growth and their special spotted and black patterns. Later, this Turing patterns was also applied in the specific phenomena where two groups of the ants they fight, and after their battle, their here and there they will put their graveyards. So their graveyards were also actually happening with a particular pattern, and animals make their special territory on the basis of that special pattern. So there are some particular evidences which was previously were not taken so much seriously, but later we get to know that all of them are following a particular reason, and they were following that pattern. These are the credits I will give. So before that, I will, if anybody, sir, Rahul sir or ma'am has seen that Enigma machine on that movie.
No, I haven't. I haven't.
So this is the Enigma machine. So in this machine, it was known to be never decoded by anybody before Alan Turing. So what German soldiers were doing, they were sending the message in a coded way. So this was never decoded before, and it was impossible to decode because every message was different from the previous message. So there you can see there are 4 wheels, and beside the 4 wheels there were 3 lights, wheels, and one particular toggle button. These 3 were working as a permutation and combination. So just at before the message, one code was there. On the basis of the code, they will toggle the button. After that button, they will see which light is blinking. Then they will see the combination of these wheels, and then they will start reading the message. So because of that big permutation combination, it was impossible to decode the Enigma machine. But we can, this is the Turing machine which Alan Turing made to decode the Enigma machine. Uh, Obviously, Alan did a very great job to decode the Enigma machine, but along with that, there was a very big and foolish mistake which German people were doing. Because of that only, he was able to decode. Because in every code, in every message, on the bottom, they were writing Hail Hitler. So at the last, Alan Turing got to know that we need not to decode the whole message. We just need to decode that last message, which is always same. So they were writing Hail Hitler at the bottom of the message every time. So they decoded that Hail Hitler message, and they got to know how they are sending that thing. So this was a mistake which German did at that time, and Alan Turing took the benefit.
I
And
just want to
yes, sir.
I just want to confirm one thing. So because the Germans were writing Herr Hitler every time, so
Yes, sir.
so this was a similarity in all the messages, and given that you can make different permutations.
Yes, sir. Actually, it was impossible because every single message, the permutation combination was different. So even though they will decode a single message, the next message it was impossible to decode again, because that 3 things which were changing every message, it was impossible. But later they got to know that at least they know some letters 100%, that at the bottom, whatever the code is, it is Hail Hitler. So they have some constants. So so with the help of that constant, they were able to decode every message. And he modified his machine according to that constants.
Okay. So
yes.
So did this happen then that Herr Hitler contained all the information they wanted to decode? Is this
not all the information, but after getting this information from that later, he modified his machine so that these constant, these later can be already reduced from the coding. Are you getting me? Means before that we have HAIL R. In Hitler T, we have 6 letters which are different.
Okay.
So at least if we know that Hail Hitler is having this particular combination, we can put that thing directly on the machine, and these 6 or 7 letters we need not to decode, and with the help of that we can guess that what is the initial combination of that 3 things, that toggle machine, that toggle switch, that 3 lights, and that wheels. We just need to know the combination of these 3 things. Later the decoding was not tough.
So
I think that, this means we are having already few letters decoded, so we can find out the pattern.
We can find out the combination of these 3 things which they were using as a particular combination. So if you will see that movie, you will get it very interestingly. So that movie we saw, me and Prakash sir, very long back during COVID situation. It was a very good.
Nikhil,
Yes, sir. Yes, sir. Yes, sir.
But Rahul bhai is asking is a bit tricky one question.
Which
Probably no, the answer you gave that is okay. But
yes,
what
sir.
I believe there is something more to that.
You can
No, no,
explain,
no, no.
sir.
I don't know even. I don't know even. So
Uh-huh.
whatever technicality you mentioned, that is perfectly all right. But when it comes to the decoding, so Heil Hitler was something after decoding that Alan Turing got some confidence in his machine. Otherwise, his lament, his colleague was
Were very
were in
very
totally
disbelieved.
disbelief
They were
and
not
yeah,
happy that he is working for a very long time and
and more importantly, I think they were at the verge of abandoned of that project.
abandoning the project. They were about to abandon.
Yes. So Rahul bhai, I think that has not been. At least I do not know historically what extra has been done thereafter by Alan Turing or anything anybody else. But that probably was the beginning of the deciphering those means messages.
Messages. Yes.
That I can
So,
say, as I can remember from that movie.
Okay.
Because
so
just because reading with best regard Nikhil, with best regard Rahul bhai, I cannot read out the entire letter, na? Because it will contain only 6-7 letters.
yes, sir. Yes. Obviously.
So at least it was a blessing in disguise, you can say. After
Yeah,
the
it was a blessing in disguise. A very cute mistake done by
yes,
German German
yes, yes.
soldiers.
But anyway, they were really smart.
Obviously, they were.
They were. They still are, but again, probably it will be seen in Third World War.
Okay. So does anyone has any more question to ask?
Yes, yes, sure.
Nikhil, are you done?
I am
Yeah.
done. Thank you is
Okay.
there.
Oh,
Okay,
I
okay.
see. I see. Because it is mentioned in various language, so I am not Turing.
So it's Japanese. You have
The
Messi. It's
Grazia
French.
first is Italian, that Vinaka is Fiji, Tarima Kashis is Indonesian, and this Tak is, I think, Norwegian.
Okay.
Then Japanese, and
And
Mercy is
Chinese.
French, and Japanese, Dhanyawad is Hindi.
And that one is Chinese, I suppose.
That one is Chinese, that the red one, I think.
Mm-hmm.
Very complicated most.
Okay. Yeah. Okay. Thank you so much, Nikhil, for such a different kind of talk.
Actually, his birthday was recently 23 June. So
Okay.
that's why.
Okay. Yeah.
Thank you so much, sir, for giving opportunity.
You're most welcome for giving this talk.
No,
So who is next?
I can't see anyone.
Should I turn my camera on? Okay, maybe I can turn my camera on.
Now I can
Oh
see.
yes. Rahul, bhai, are you in space? You are in 4D.
No, I'm not in space.
He has made himself already.
Okay. Because nowadays it is very difficult to imagine